In the last video, we talked about equipartition theorem, degree of freedom, and the internal energy. And then we could calculate the internal energy in a crude way from the degree of freedom using the equipartition theorem. For a monoatomic molecule, the internal energy is 3/2 kT, which is supplied from the 3 motional degrees of freedom, which is only translational for the monoatomic molecule, multiplied by half kT per degree of freedom. So we have the internal energy for the monoatomic molecule as 3/2 kT per molecule. For the diatomic molecule, it's 5 from 3 translational degrees of freedom and 2 rotational degrees of freedom. It is 2 because it's a linear molecule, multiplied by half kT, so we have 5/2 kT. And for the linear polyatomic molecule, the internal energy is 5/2 kT. Same thing with the diatomic molecule, because it is linear, so it has 3 translational degrees of freedom and 2 rotational degrees of freedom. And in all this, we have ignored the vibrational degrees of freedom because vibrational states are not occupied at room temperature. So for the nonlinear molecule, it has we also talked about the internal energy for the nonlinear molecule. It has 3 translational and 3 rotational modes, so that makes 6 times half kT from the equipartition theorem. Apologies for that, it's not equipartition theorem. So that's 3 kT. All the above is just to describe the internal energy of an ideal gas, and that's because for an ideal gas, the internal energy depends only on temperature. For real gas, this gets more complicated. The internal energy depends on more than the temperature only. However, it's important to note, if we look at it, the internal energy is 3 kT, 5 kT, 5/2 kT, 5/2 kT. So it increases with temperature. Even for real gases as well, it also increases with temperature. Okay, the internal energy as described is the system's internal system capacity to do work. It can be changed by doing work on the system or when the system does work on the surroundings. It can also be changed by adding or removing it. So that's by changing the temperature using whatever means. What is work? Work is energy transferred, so it's a form of energy transferred across the boundary. Remember, the system is separated from the surrounded by a boundary. So work is energy transferred across the boundary of a thermodynamic system during a change in its state. So the change in its state can be brought about by anything. We'll talk about that so quickly. So during a change in its state, and can be completely converted to a change in height or lifting of weight through a distance. So in general, work is a force that causes a mechanical displacement on the body. It is given the symbol W. We have different types of work: the lifting work, expansion work. Lifting work, that's mass times gravity. So there's a pressure that's forcing the mass to move a certain distance, dh. Expansion work, pressure forcing a gas to expand in a certain volume. And we have the surface expansion one, that's the surface tension, forcing, which is the force causing a change in area. Then there's the tension causing a change in length, that's extension work. And electrical work, that's electric potential force causing a change in charge. So work in thermodynamics, when it's done by the system, it is negative work. It is negative work because it means that the system loses some internal energy, so the internal energy reduces. If work is done on the system, then it's positive W, and this is the convention in the chemistry world. So work is a path function, which means it does not depend on the state of the thermodynamic system, but more like on how the system was achieved, whether it's lifting, expansion, extension, or other forms of work. So heat is another way in which internal energy can be changed. So heat, given the symbol Q, small letter q in this case, that's the amount of energy, same thing, it's energy, that is transferred through the boundaries of a system during a change in its state as a result of a difference in temperature. And in a similar way, when the system loses heat, so that's when heat is transferred from the system to the surroundings. When the system loses it, Q is negative. When the system gains heat, that's when heat is transferred to the system, Q is positive. Heat is a path function. It's a process. So it's a process where heat energy is transferred. So it's not an entity, it's a path function, meaning that it is independent of the current state of the system. The internal energy, work and heat are all measured in joules because the internal energy, work and heat are forms of energy. So the SI unit for everything is joules or kilojoules. Other units that can be used are the calories, the erg, and electron volts. The calorie was initially used only to measure heat and ergs for works, but since they are both forms of energy, it can be used interchangeably. 1 calorie is 4.184 joules, 1 erg is 10 to minus 7 joules, and 1 electron volt is 0.16 times 10 to minus 18 joules. Okay, so let's put all this together in the work, heat and internal energy. Recall, the internal energy is the energy processed due to the motions, internal motions, and spatial arrangement. The first law, we already talked about the zeroth law of thermodynamics. That's related. It has to do with thermal equilibrium. So we move on to the first law of thermodynamics. The first law of thermodynamics is related to the law of conservation of energy. It's actually a form of putting that law into equation, into mathematical expression. So when we remember law of conservation of energy, energy cannot be created or destroyed. It can only be converted or transferred or transformed from one form to another, from the different forms of energy. Whenever amount is used up, an exact amount, whenever one form of energy is released, an exact amount must be used up somewhere. So which means if a system loses internal energy, the surrounding gains it. Delta means change in. So the change in internal energy of the universe is a change in internal energy of the system where we're working on, and plus a change in the internal energy of the surrounding. So because energy cannot be used up, so the internal energy of the universe is always zero. The universe is the totality of everything. When an energy is created somewhere, energy is released somewhere, it is used up somewhere else. So, putting this in a mathematical statement, it says that for a closed system, the change in internal energy of the system is equal to the change in the heat plus W. So that's when we're dealing with small change. So du equals dq plus dw. If it's a macroscopic change, so delta U is simply Q plus W. So change in U is the amount of heat supplied plus the amount of work done on the system. Okay, so please, I just want to quickly emphasize this. It's for a closed system. It's fit for an open system where mass is allowed to be exchanged. The equation is not correct for an open system, but emphasis for a closed system. And this is because its own energy is allowed to be exchanged in a closed system with the surrounding. Okay, so we introduce the processes in thermodynamics. Remember, thermodynamics studies energy changes. So a process is any form of occurrence that changes the state of the system. Any occurrence that changes the condition of the system, that changes the different variables of the system. So it's for example, in chemical reactions, what can be in several forms. So if electrical surge is passed through a system, the process has occurred. If pressure is applied to the system, a process has occurred. If heat is allowed to be transferred, temperature change, heat supplied, a process has occurred. At this point, we need to remember that the internal energy and enthalpy for an ideal gas is a function of temperature only. That is not the same for a real gas. So a process can be carried out under certain conditions. It can be carried out at constant temperature, constant volume, and then we have different equations arriving from that. We will consider each of these conditions separately. Then a process can also be done reversibly or irreversibly. So a process can be carried out reversibly or irreversibly. When we refer to a reversible process, it's a slow process, and maybe not quite right, it's often called a quasi-static process, such that each step is carried out in a very, very infinitesimal amount, and the steps are in equilibrium with each other. So a reversible process can easily be returned back to its initial stage. And an irreversible process, which is usually what occurs naturally, the property of the system changes by a very large amount. So, and the system and surroundings do not return to their condition once the process is initiated. So reversible, a very slow process, very, very slow process, and an irreversible process, a very fast process. So we'll be looking at pressure, volume, work. So let's quickly introduce pressure, volume, work, and then we'll consider the different conditions in the next video. So a pressure, volume, work is work associated with chemical change when the volume of the system changes as a result of the disappearance or formation of a gaseous substance. That's because it's gases that expand to fill the volume. So this is usually called expansion work, but it can also include compression work, which is associated with negative changes in volume. So W will be positive in such a situation. Mathematically, the W is the differential of W, that's change as it happened, is given as negative external pressure multiplied by dV. So if we integrate, this equation, so this becomes W, and then we have minus V1 from initial stage to final stage, P external dV. So depending on how P varies with V, whether it's a reversible or irreversible process, that depends on how much the exact form of the equation. So we'll continue in the next video.